Okay, welcome back. We're still trying to get our linear actuator final project, ME421, dynamic systems and controls. We're doing the controls part now. And so what I'm going to do here is I'm going to put a schematic diagram of the linear actuator that we're going to be using in our system. I might show you also the actual linear actuator that we will be using in our system. And one of the things is I'm going to do a schematic diagram of that now. This we talked about in class several times, and you can go back and look at some of the notes. And so what I've got here is I've got a motor that's driving a belt and pulley. And on that belt and pulley, it moves this position X. So this motor goes back and forth. There's no gearing or anything like that on it. And then I don't have a black. So, you know, there's two colors that have to come out of this. I say red and black, but, you know, I don't have red or black here. So we just put our voltage in here. This is V in. That's the voltage to the motor that we're putting down. Okay, and so suffice it to say that I can suppose that I do the lab you did in the regular class lab, if you did that. I would go through all the trouble of trying to develop what the dynamics for the electric motor are. I could look at my previous notes, and it would be Km over Rm. It's the gear ratio, N, divided by J equivalent S plus B equivalent. So we have to go back and look and see what all those different parameters mean. We have to see exactly what they all mean and what that. But from a block diagram perspective, if I put volts going in, then what I get is omega of. So in this case, it's not even omega. I can just go ahead and say, oh, by the way, this is x dot. This is the velocity. In the lab, you did angular velocities, but see, we can convert between angular velocities here, which is this, let's call this plus theta, and all we really need to know here is what is this r, and then we can say x equals r theta. So we can convert back and forth if we need to. But suffice it to say that I'm going to take this model. Now, if I'm not, in this particular case, I'm interested more in the position. So in the end, I'm going to want to hook the position together. And so I'm going to put the other integrator on here to get position. But for now, first I'm going to do the experiment in lab that you did in the class. If you went to the class lab, you did this experiment. If you didn't go to this class lab, here's what they did. They put an input of some constant volts. So one thing that you could do, you certainly could do this experiment, right? You could put an input at 1 volt, and you could find out what the velocity is, velocity 1. Then you could put 2 volts, and you could find out what the velocity 2 is. And what that would tell you then is what is the steady state gain for this system. This would tell you that for the open loop system, G S equals 0 is going to be Km Rm N over B equivalent. There's a lot of things you could substitute in there, but you don't have to substitute in, because what you've done is you've made a 1, 2, 3, 4, 5, 4, 3, 2, 1. You've put in volts, and you've gotten out meters per second. You'll see that it's a straight line, and you can figure out what the slope is. The slope of that straight line are all those numbers put together. That's what the slope is. You say 1 volt, that's how many meters per second we get. 2 volts, that's how many meters per second we get. Okay, so you can just do it experimentally and you're good. Sorry, I dropped one of my pens. The red one. I dropped the red one, so I had to get that. Okay, so the other piece of the experiment that you did in class, in the lab, was as you put in this constant voltage level, what you did is you watched the dynamic response time versus the velocity. You watched the time versus velocity, and what you could see is that this went, so this would give you the time constant tau. It would give you the steady state value of that. Oh, sorry, yes. Okay, so then we give you the steady state value of that. Well, we already know what the steady state value of that is. I'll put a star here, right? This is the steady state value, right here. But what we're interested in is in the time constant, so we could find out what the time constant was. And what we could do, because we're interested in the time constant and these sorts of things, what I'm going to do is I'm going to make this look a little bit different. Vn, I'm going to put this here, and I'm going to make this is going to be Km. No, let me just throw in all the substitutions I'm going to do. C over tau s plus 1. And this is omega, x dot. Okay, what is C? Well, in this case, we can just write it down. Let's make sure we write it down somewhere. So I use different colors to write stuff down here. Let me use orange to write that down. C is equal to Km over Rm n over JB equivalent. Okay, that's what C is. But we don't care what it is. We have a value for that. We have a value for that because we got it off the slope. We got the slope off of this graph that we just made. So we already know what the number is. And I'll tell you what that number is. It just turns out that that number is 0.17 meters per second per volt. All right? You can check all the units. They're all good. Okay, you should check all the units to make sure they're all good. Now, we also need to know what the time constant is. And what we're going to do is we're just going to measure the time constant, and I'm just going to tell you what the time constant for this one is. Time constant is 0.028 seconds. So now we know. Everything in that block we already know. Now, we know how to do control system stuff, but there's some things that we have to do. So let's see, we got everything now. We've done our experiment in the lab. That's why we did the experiment in the lab, was to start learning a little bit about how to characterize our motor in the absence of any specifications, because there aren't any specifications for this motor. And so now what we're going to do is we're going to start talking about, I wonder, I'm going to go ahead and put this on here, 1 over S. So now what we're going to do is, I forgot, there's a lot of things here. Well, let's just try and do it as in broad brush ways as we possibly can. What I'm going to do is I'm going to say, I am going to use the Arduino Mega Motor, and I guess I'm going to send you links to specifications. Like, you can't find Mega Motor Shield. If you can't find Mega Motor Shield on the internet for Arduino, you can't find it? Oh, that's fine. You're fired. Okay? Sorry. Harsh. Cruel, but fair. Okay. So we're going to look at what the Mega Motor Shield is. So it turns out there's a lot of nuances. If you want to know nuances, get me started on that some other time. But what that basically does is you send out a 0 to 255 number. That is a 2 to the 8th bit number. Now you'll notice that I wrote that word in lowercase because 2 to the 8th bits, that's 2 to the 8th. Remember I said if we're using 2 to the 10th, I'm going to make it capital bits. You're going to send out a number that's 0 to 255, and you're going to send out another number that says its direction, and that's either plus or minus. And if you look at that, there's something that says that this is really a 2 to the 9th bit number, but I'm going to leave it here. So really, what I am allowed to send out through this Mega Motor amplifier, this is essentially an amplifier. What I'm allowed to send out with this amplifier is I can send out effectively plus 255 if I want the motor to go positive direction, depending on which wire I put the positive voltages on, or I can send out minus 255 if I want the motor to go backwards in the negative direction. Right? So I can send out 0 to 250, I can send out plus 255 or minus 255. That's in bits. Now, I also need to measure, the position of this thing. And it turns out that what we've already done is we already know that there is a gain for the potentiometer that says this is, so there's one part of it that says it's 1023 bits for 5 volts. So if your potentiometer reads 5 volts, it's 1023. If it reads 0 volts, it's 0. So it's 1023 bits per 5 volts. Now, I invite you to measure the length of this linear actuator. It's 0.1 meters. And so there's a gain there that says, oh, by the way, this is 5 volts. So when it's at one place, it goes 0.1 meters. So there's a different gain, right? Okay. And so now what I'm going to do, there's a lot of different ways of doing this. And what I'm going to do now is I'm going to slowly go through and figure out exactly what do I need to send out to I'm going to send it out to my motor to make it move. And so what I'm going to send out to that motor is I'm going to send out bits. I'm going to send out bits, and I'm also going to send out the direction. And so what that means is when I send bits to my motor, I'm just trying to manage my board space over here because I'm already getting close to that edge. So when I send out the right number of bits to that motor, it turns out we're going to use a 9-volt. We're going to use a 9-volt battery, and what that means is that our power amplifier is going to give us 9 volts for 255 bits. Okay, so we've got a block there that says 9 volts over 255 bits. So that's a piece, that's a gain. It's a natural gain that's built into the system because of the hardware. It's the power amplifier gain. We have to take that into account. Okay, I'm going to go ahead here. So once I get volts coming out, I can go back over here and look. This is C over S, tau, S plus 1. Right? I've got those numbers there. And what that's going to let me put out here, this is in this, if it's okay. So I could break this. Yeah, let me just break this up. I know I'm getting dangerous. I am getting dangerously close. 1 over S. This is X dot, and this is X. So I know that if I move this thing, okay, hold on a minute. I'm going to move this whole thing over to here. I'm going to get a glass cutter, and I'm going to move it from here over to there. So, okay. And voila, there it is. I've just moved it over. So now I'm going to go ahead and put in here. So this, if I move this actuator 0.1 meters, I get a change in voltage on my potentiometer of 5 volts. So that is 0.1 meters per 5 volts. This is the potentiometer. I may have misnamed that earlier. Now, when I read the potentiometer, I also have to do an analog to digital converter. So the analog to digital converter gives me 1023 bits Sorry. Okay, everybody's a critic. All right, sorry I did this the wrong way. This is 5 volts per 0.1 meters. If you'd have checked your units on this, you'd have seen it. You can't multiply X, which is in meters, right? X is in meters, by something. This gives me volts out. My analog to digital converter gives me 1023 over 5 volts. So these are all natural gains that are built into the system, and what that gives me is bits out. Now there's a lot of different ways of doing this, but in our microcontroller, the easiest thing for us to do is to decide how many bits do you want it to go. So we're going to do bits desired. Now, you know, I can tell you this over here, I know what the range of this bits are. It is 1023, that's the maximum, and it's 0, that's the minimum, right? So over here, when I tell it to do something, there's no sense in telling it to go outside of this range, so I'm just going to either tell it 0 to 1023. So this is, again, I'm going to tell it to go 1023 or 0. And one of those is going to be telling it extend all the way, and one of it's going to be saying retract all the way. There's a lot of times when I go to some trouble here, instead of making this go from 0 to 1023, I subtract 512 off of it so that it goes plus 512 to minus 512. So in a lot of control applications, you like to put the midpoint of your actuator at 0, because there's a lot of times when you say, hey, actuator, go to 0. And the 0, you want that to be at the midpoint. So I might do it that way. And then I'm going to use this as my control law, right? I know what my control law is. It says, hey, I need to go out and find how many bits there are. I need to find out how many bits are there. And this gives me the error in bits. That's my bits error. And now, you know what I need. So this error in bits, suppose that my desired bits is 0, but my actual bits is 1023. Then that's minus 1023. And now suppose that my desired is 1023 and my actual is at 0. That gives me plus 1023. So the range of that goes from minus 1023 to plus 1023. And so, you know, if the number of bits that I need to send out is plus 255 to minus 255, that's because this analog to digital converter, all it does is it sends out a voltage that's proportional to a number between 0 and 255, and it either has one more bit that tells it it's either plus 255 or it has a bit that tells it it's minus 255, okay? So it's one of those two things, that's how it's going to work. All right, so now I can see here that there's, you know, I haven't done my whole control law because I do have to put my KP in there for control law, and then that gives me the command. But you know, if I send out a command, that is, if I send my command out in bits, but I need to convert it to bits, that's the conversion factor. 2 to the 10th to 2 to the 8th, that's divided by 2 to the 2nd, or 1/4. So these are all just natural gains that are in your system. The ones that we know about, like we've gone through all the trouble to find out, like, oh, what's this gain here, right? This is the motor. That's all fine. All right. I've got this block diagram that, you know, you can look at it skeptically and say, yeah, maybe he did that okay. You know, somewhere in a computer I have this number of bits, but, you know, I can convert this number of bits into x in meters. I can convert that to x in meters by the same thing that turns out that this is x in meter to bits, right? This is x to bits, and I'm looking for bits to x. So really what I want is 0.1 over 1023, right? 0.1 over 1023. Now, the problem is now I also might like to know exactly what my, so I'm going to erase some stuff here, sorry, what my x desired is. Well, if I want to know what x desired is, I have to do kind of the same thing here. What I have to do that is I have to say, it's 1023 bits for 0.1 meters. So I have gains on either end of that thing. Sometimes I have to worry about that stuff. What you can see is that in the end, I just converted. So even though I wrote my whole first set of control laws from bits desired to bits, because that's what I'm doing in the computer, I also keep track of what the fact that the x desired has a gain to it, and the x measured also has gains to it. And it's easy to see that, like, once you're in block diagram world, like, these block diagrams can move wherever you want. So I'm going to take this block diagram all the way over here and just cancel the two of them out. And so what I really need to do now, is I need to multiply this whole thing together. And so what I'm going to do is I'm going to call this k at the top. This is going to be the constant. It's going to be 1/4, 9 over 255. It's going to be whatever that c value is. Did we get what c is? It's going to be times c. And then this is going to be, so if it's okay, I'll just do this. This is times 1023 over 0.1. So I'm going to multiply and figure out what that k value is. It turns out I've done that multiplication. You can do it too. It's 12.8. It's 12.8. And then we already know what tau is. So really, if I just go back down here, and I'm going to change this, I'm going to make sure I got it in the same form. Yes, I do. I'm just going to change this, look, to k, right? And I've done all this stuff experimentally, right? I found out what the c was experimentally in the lab by finding out what the time constant was. I find out what the constant steady state velocity was in meters per second per volt, so I did that in the lab. I kind of measured, I can go back and get my voltmeter out and measure that I get 5 volts. If it moves 0.1 meters, I get 5 volts out of it. And then I also know how the analog to digital converter works, and I could test that too. Analog to digital converter 1023 over 5 volts. This is a minus sign. I noticed I just left that out. So I'm all set to go here. In fact, not only am I all set to go, I have my block diagram right there. And all I really have to do now is in this block diagram, which I have numbers for every one of these things, I just have to put my control law in here. Kp, uh-oh, I'm falling off the edge here, plus, minus. I hope you can kind of see that on the edge. This is figure 10.29 in the Ogata book. Go look at it. Oh, same thing. Now we have a control system. We have our controller. We're all ready to go. We're set, baby. Let's go. How do we make this thing work? Well, it turns out there's a number of different ways to do it. But one of the things that we can do is just find out what the closed loop transfer function looks like. In this particular case, it's Kp, K, over tau s plus tau s squared plus s plus Kp. All right, you know what I'm going to do here? I'm going to make my denominator here. I'm going to put my denominator so that it is in canonical form. Because then I know that omega n squared is going to be Kp over tau times, oh, that's it, Kp over tau. And then I know that 2 zeta omega n is equal to 1 over tau. So 1 over tau, so we can figure out what 2 zeta omega n is equal to 1 over 0.028, which is, this is 36. Sorry, 36. 2 zeta omega n is equal to 36. If I put numbers in here, this is s squared plus 36s plus 12.8 times Kp. So those are the numbers for that. And so 12.8 over, all right, so this is Kp times 457. So I know nobody's told me what zeta should be, so I'm just going to choose zeta equals 0.707 because there was a whole big diatribe in lecture about that, why to choose zeta equals 0.707. And then what I can tell you then is that 2 times 0.707 times the square root of kp times the square root of 457 is equal to 36. And I'll leave that as a trivial exercise to the students. It's not quite. I just rounded that number to 1.5. So that means this number here, kp equals 1.5, what I expect to have happen is that a time response for this ought to be really nice. It ought to be really nice where the settling time, I ought to be able to I ought to be able to predict the settling time. I also know that there would be about 5% overshoot, and that should all act very nicely. And you'll see later in experimental work, it doesn't quite come out that way. Part of the reason is if you look at this whole block diagram, do you see friction anywhere? No, you don't. And what does friction look like? Friction kind of looks like damping. So if we added more damping to this whole business, we would change all our numbers just a little bit. But this is a good place to start. Theoretically, this is a good place to start. If you're close, it'll be good. If you're 1 order or 2 orders of magnitude off, you will find that out. And guess what? If you forgot to put this gain on it right here, well, you'd be you'd be 2 orders of magnitude off if you forgot that gain in there. Then you'd know something was wrong. You have to go back to the drawing board, okay? So this is what we need to do. We need to get all the wires hooked up just the right way. There's some background and all that sort of thing that we have to figure out, and we'll do that. But this is the theory behind it. Now, it's rather disheartening. It's rather disheartening because you're going to find that this doesn't work very well. And then you're going to say, well, what am I supposed to do? And then I'm going to tell you the secret. Shh. Secret. Remember, use the P knob, right? And you start with P equals 0. Then you move it to P equals 1.5, which is what we think it should be. Yeah, it should work okay. Then you might change it to P is equal to 2. P is equal to 5. Stuff like that. So you keep making the P a little bit higher. So that's the secret, is that any bonehead, once you get this control structure put together, any bonehead can make that work, okay? So now I'm going to tell you finally, and we'll want to change that. Now I'm going to tell you one last thing. So here is the thing. You have to make sure, you know what, I'm going to step back, take a little bit of a minute here, and I'm just going to get rid of I'm going to make some extra space for myself, okay? All right, poof. Did you see how fast that happened? I should be a window washer. Okay, so in the lab, here's what you need to do. You need to first connect the potentiometer. There's 2 of them. Right? There's one of them, there's one that's hooked to the motor to measure the motor position, and there's one that we're using as a command. And so the one that we're using for the command here, you have to make sure that you've got it hooked up so that when you move it 0 to 0.1 meter, here's the command. Command pot. When you move it to 0, you want it to say minus 512 bits. Right? And when you move it to 0.1, you want it to say plus 512 bits. Okay? And then you want your feedback to do the same thing, minus 512 and plus 512. So when you move, so disconnect, don't put power to Don't put power to the amplifier. Just hook up the potentiometers with no wires hooked to the motor. This motor wires are disconnected, and move it around. You say, oh, I moved this one all the this way, this end. I moved that one all the way to that end. You've had some experience hooking up potentiometers. That was in the first lab that we tried to do, right? So that's why I had you do that. Now you're going to have both of them hooked up. You've got this part of the structure more or less put together, so you know what your desired bits are, and you know that you have this stuff set up the right way, right? If you have a SIGN flipped here, you're going to have some trouble, right? You're going to have some instability. All right, so then we need to hook up our motor, and what we need to do is that out of the amplifier, there's an A and a B. And what you want to do is you want it so that when you put into the amplifier, well, if you put in 0, you want no voltage to come out of the amplifier. If you put in plus 255, you want this to be plus 9 volts, and this to be minus 9 volts. Or, sorry, you want this to be plus 9 volts. You want A to be plus 9 volts, and B is ground. I'll just put that there, G and D. But on the other hand, when you put in minus 255, when you put in a minus 255, which it may be that this direction means one thing or another. When you put in minus 255, that means that you're going to have the ground here, and this is going to be plus 9 volts. What this means, let me make sure that I write this like this means when you do this scenario here, you want this set up so that the motor moves out, right? So when you tell it plus 255, you want the motor to move in the positive X direction, because if you give it plus 255 and the motor moves in the minus X direction, that's a minus sign, that's bad. Okay, when you do this one, you want to make sure that the motor moves in, right? So once you have those two things set up, then now you can connect your motor wires up to the A and B. It turns out there's little buttons here for this, and you can push those buttons and it makes it move out or back or forth. So there's a way of checking that. But so the first thing is you want to make sure you get your potentiometers hooked up, and that might mean, because I can tell you there's some mistakes. Oh, I forgot. There's some mistakes on my prototype boards that those motors are soldered to, and they're all of the potentiometers. First of all, each of the linear slides that you see there has 2 pots on it. So now each one of those potentiometers actually has 3 times 2 is 6. It has 6 different wires on it. So you have to pick the potentiometer. You have to make sure that you know which one is the ground and which one is the plus 5 volts and which one is the wiper. You know, if you get it wrong, it doesn't hurt too much. You can always put a minus sign in the software. That's okay. But you have to do that for both of the potentiometers and make sure that they're working. The second thing you're going to do is you're going to hook up your motor with your 9-volt battery, and it's going to make that thing move back and forth, and you're going to be good.